Welcome to the 11th episode on my series Introduction to Physics. Today we are going to focus on a new topic, which is thermodynamics. And we'll start slow, we'll talk mostly about the equation of state. So let's get on with it. The living room of a house has a volume of V equals 100 meters cubed and normal air pressure of P0 equals 1013.25 hectopascal. The cold air of temperature θ1 equals 15 degrees is warmed up to θ2 equals 25 degrees Celsius without increasing the pressure. A. What is the air density before and after heating? B. How much air leaves the room? And C. What happens to the air pressure if the room is fully isolated? So, what values and variables can we take out of the text? We have given the volume of the room as V equals 100 meters cubed and the normal air pressure as P0 equals 1013.25 hectopascal. Now, hectopascal is not the basic unit, and let's be honest, it's easier to do it now. So let's calculate this now into Pascal, and in order to do this, we have to multiply the value with 100. So P0 equals 101,325 Pascal. In addition, we have given the two temperatures, the low temperature θ1 as 15 degrees Celsius and the higher temperature θ2 after warming as 25 degrees Celsius. Again, both of these temperatures are not in their basic units, because if we want to use temperature for calculation, we need to transfer degrees Celsius into Kelvin. So from θ1 follows T1 as 288.15 Kelvin and T2 as 298.15 Kelvin. And we are searching for, first of all, in point A, the density ρ1 and ρ2 before and after heating. Secondly, in point B, we are looking for the amount of air that's leaving the room, let's call it delta M. And in point C, we are looking for the pressure P2 if the room is heated but under constant mass. So how do we approach this problem? In general, we know that in thermodynamics, the equation of state holds. This equation states that for a given amount of substance contained in a system, temperature, volume, and pressure are not independent quantities. In particular, the ideal gas law holds if we consider an idealized system. And this gas law states that the product of pressure P and volume V equals to N times R times temperature T. But what are N and R? Well, N is the number of moles of a substance, and R is the ideal gas constant. And as the name suggests, it's a constant. So we know that R equals 8.3145 joule per mole and Kelvin. But what in detail is N? I just said that it's the number of moles of a substance. But usually when we calculate something, we are considering the mass of some substance. So can we relate N to the mass M? And the answer is yes, we can. And there is an easy relation. N times R equals M times Rs, where M is the mass, and while R is the universal gas constant, Rs is the specific gas constant, well, of a specific gas, as this name suggests. And yes, we can relate those two R's with Rs equals R, the universal gas constant, divided by M. Well, now we do have a new problem. We need this uppercase M. And this is in particular the molar mass. And lucky for us, the molar mass is a constant. And if we assume the room has dry air, then M equals 28.949 gram per mole. If the air is not dry, well, then this value would be slightly smaller, but since nothing else is given, we can assume some dry air. Is this enough? Yes, it is. So we may have just introduced a couple of different variables and equations, but if we put all of them together, we see that the product of pressure P and volume V equals to M, the mass, multiplied with R over M, both are constants, and multiplied also with the temperature T. So we basically have the relation between 4 variables, and in addition we have these 2 constants given. Hence, in our particular case, we can say that before warming, we have P1 multiplied with V1 equals M1 times R over M times T1. And the initial pressure P1 was given as the standard pressure P0. And the only unknown variable is indeed the mass M1. But we were not searching for M1. We were actually looking for the density ρ1. But this is not too complicated now, because the density of a material, in this case ρ1, equals mass M1 divided by the respective volume V1. And if we introduce this into our above equation, then the density ρ1 of our air equals P0 divided by T1 multiplied with M over R. And since the pressure P0 as well as the temperature T1 were given, we can just take our values. And if we take our values in their basic units, then we can just put all the values into the calculator, and what we get is that the density ρ1 equals 1.22. But what is the unit? If we look into the first line, we see that, for example, the unit of temperature Kelvin cancels out. We see that in addition mole cancels out. So what we have left is Pascal times kilogram divided by joule. And I'd like you to test it. What comes out of it? Well, it has to be kilogram per meters cubed, exactly the unit of density. So ρ1 equals 1.22 kilograms per meters cubed. And since this has been working out so nicely, we can do the second density also, because we do not need a new equation. We were looking for the density if the room is heated up and the pressure was supposed to not increase, which means that density ρ2 equals P0, now in this case divided by T2, multiplied again with M over R, and if we put all our given values in their basic units into this equation, then we get that the density ρ2 equals 1.18 kilograms per meters cubed. And we see indeed that heating up the room under a constant pressure reduces the density of our air. So this reduction in density leads us right away to our second question, which was how much air leaves the room? Because if we have reduced the density, apparently some air must have left the room. So we are looking for delta M. What we know is that in addition to a constant pressure, the volume of the room is of course constant. The walls are not moving. So delta M is basically just the mass M1 that we had initially in the cold room minus the mass M2 of the air in the slightly warmer room. And we know that in general, the mass M, let's give it an index I, equals ρ I, the respective density multiplied with the volume. And since our volume is constant, it's just V. But this makes it really easy because this means that delta M equals the product of ρ1 minus ρ2 and the volume V. And since volume V was given and we've just calculated the densities of cold and warm room, we can just take our values, put them into this equation, and what we get is that the difference in mass between the cold and the hot air is exactly delta M 4 kilograms. Are we done yet? Well, no, there was one final question. We were looking for the air pressure in an isolated room. So we are assuming that not just the volume is constant, but those 4 kilograms that we've just calculated are not leaving the room. What does it mean for the air pressure? Well, in this case, the ideal gas law still holds. And while this is the general form, as you can see it here, we want to substitute our variables with the variables we have. So P, in this case, was the P2 that we were looking for under the assumption that the mass M is constant. The volume V, well, it's constant as well, and it was given. On the right-hand side, we have the mass M1, the initial mass that we want to heat up now. We have given R over M, which is still constant. And in this case, we need to introduce the temperature T2. So we are warming up the mass M1 to the temperature T2 without any loss of mass. And since we are looking for P2, we can write this equation as P2 equals ρ1 multiplied with R and T2 divided by M. And yes, I've just introduced the density ρ1 in this equation because if you look up, you see that we have M on the right-hand side, V on the left-hand side of our equation. And if we divide this equation by V, we get on the right-hand side the density ρ1. And if we take all our values using the basic units, again, we can calculate P2 right away. And what we get is that P2 equals 104,471 Pascal. And yes, this is, of course, larger than P0. So it means that under a constant volume and in an isolated system, heating up the air means increasing the pressure. So all in all, you can see here that this ideal gas law, of course, it's an idealized system, but we can consider some amount of substance and actually relate pressure, volume, and temperature to one another. What does it mean in general? Well, if you go out into the world and you open your fridge, you may actually realize that, yes, this has to do with this ideal gas law. At least if you open it, you close it again, and you realize that you cannot reopen it easily. If you're interested in this particular case, I'll leave you a link below in the description because I've already uploaded a video with this topic. On the other hand, if you plan on flying soon, well, let's test this ideal gas law. Just take a bottle of water, a plastic bottle, and if you're up in the air, just drink it half empty and reseal it. And then have later a closer look at it after you've landed. And let me know what you observe in this case. And with this, I would like to thank you for your kind attention. I hope it was helpful. And if it was, leave a comment below, give me a thumbs up and consider subscribing. And then I hope to see you soon for another video. Thanks and bye.